Um, this is our last KCS talk for this semester. Um, we have small audience today. I hope that more people will come. Okay, in just a few seconds or maybe just a few minutes. So anyway, our speaker today is Mr. Karki. He's a third-year PhD student. His advisor is Dr. Haibo Wang. The title, as you can see, of his talk is Distributed Non-Duplicated Sampling with Application of Network-Wide Flow Cardinality Estimation. Okay, let's give Mr. Karki a warm welcome, for his talk. It's going to be an interesting talk.
Well, thank you so much. So, as Dr. Chang said, my name is Aayush Karki. I'm a third-year PhD student here in computer science.
You
Yeah.
You guys speak up.
Speak up. Okay.
You have to speak up.
Okay. Sounds good. So, my research focus primarily focuses on networking topics, data streaming algorithms, and so this is my kind of specialty where I focus on machine learning to enhance the performance of these streaming algorithms. So the main research project that I'm following is network measurement tasks. So where I perform different tasks in network that will get some statistics about how the network is performing. And next is like I want all of the algorithms that I implement in like network tasks, like the one that I did for this project, I want it to be suitable for hardware settings. So we have some P4 switches that are available in Fabric that I am currently trying to learn and use to deploy all of our software algorithms in hardware, so it is compatible with it. And finally, this is another work that I'm doing where I try to enhance the performance of the data streaming algorithms using machine learning, where I get the post. I'll hold. Okay.
You either have to speak up or they have to do something.
I'll speak up. Is that okay? Okay. So and finally, like the final work is like machine learning, using machine learning to enhance the performance of our data streaming algorithm, where I get the estimate from the streaming algorithm and use machine learning after the fact we got the estimate and enhance the performance of the estimate even more. So that's some of the work that I focus on. Next slide. So this is the overview of what I'll be covering. So I'll give you some background related to my work and focusing on my algorithm and showing some of the experimental results that we had when we were doing experiments. And finally, the hardware implementation. This is relatively new thing, and I'm still working on the part, but I'll still present some of the few results that I have generated like in past few months. And finally, some conclusion and future work for myself. Okay, so to start up, so in current network scenario, like this is a simple topology of a simple network where we can see like if a packet has to travel from one point to another point, it has to go through different points before reaching the destination. For example, here in this figure, host A, if host A wants to send packet to host D here, host A to host D, it has to go to switch 0, switch 1, or router, and then switch 1, and finally reaching this destination, right? So it has to travel through multiple points, right? And so along its way, the switch, the router, and like other devices that are in the network, they are very limited in resources, as in like they have limited processing power, limited storage, and limited memory. So we have to have some sort of algorithm that is very compatible with this setting. This is where the work comes in. So anything that we do will be working on that switch label, like in the router where the memory is very limited. So not only that, but also knowing like how a packet flows from, or packet travels from one point to another. We need to know how it works. And also there are some other applications related to it, like how we can enhance the performance of the network, like how we can remove congestion, how we can avoid loops. So for that, we need some statistics. So collecting such statistic is network traffic measurement, right? So, and like when we implement our algorithm, it is very difficult because first of all, we have limited resources, and we want to make sure that our resource fit in there and does not affect the line rate of the targeted switch, right? And if it affects the switch performance, then there is no point of implementing, because the switch is already limited in resources and it will cause more congestion to it. So, next slide. So as I said, like doing this is very essential for three main reasons. Like one is for monitoring how the network is doing. The next is mainly for security reasons, like we want to have our network to be very secure, and finally to boost the performance of our network. So so there are many applications. I have listed few of them here. So each of these applications have a specific pattern associated with it. So for example, here in DDoS detection, so what happens usually is like multiple sources are sending packet to a destination. So usually there is an attacker who is controlling multiple botnets and trying to attack a target server which is trying to serve legitimate users. But because of that, it does not. So the pattern would be like there will see many sources trying to attack one destination. For the next one, port scanning, we'll see something like one source trying to abuse like several ports to see which ports are open. So it would be like one source trying to go to different ports. And finally, SYN flood is simply like if there is a massive TCP sync request, like incomplete ones, like where there is incomplete handshake, then we would detect SYN flood attack. And some other examples include like on the better side is like how we can see, like we know there is traffic in our network. So what can we do to know about the traffic so we can enhance it? So that's where traffic engineering comes in. So if we see the traffic volume today, like if say we have a number of traffic today, then what will be the traffic volume tomorrow? So based on that, we can allocate our resources for capacity planning. And also like other factors, like we can optimize the network using all this knowledge. Okay. Moving on. All right. So as we saw on the last slide, so different applications have a specific pattern related to it, right? So like on the left side, I've listed some of the tasks that are related to distinct base. And the next one on the right side is size volume based task. So on the cardinality estimation, usually we want to see distinct attribute associated with that flow. So what that means is like in DDoS attack that I mentioned earlier, so we want to count distinct source, so I need to change that, distinct sources associated to that destination. And for identifying spreader, we want to see which sources are trying to go to different IPs in the destination. So that would be super spreader identification. And from the size side, like that I mentioned earlier for traffic engineering, we want to see the traffic volume. So that task would be essential for those applications, for load balancing and traffic engineering, and so on. So, and finally, my work will cover flow cardinality estimation for this paper, but I'm working on other tasks related to getting the size estimate, getting the top K values, getting heavy hitter detection and super spreader identification. And for this paper, for the extension part of this work, I also did additional a task on super spreader identification. All right. So as I mentioned, flow cardinality is simply the number of distinct attributes within a flow. So this is a simple example of DDoS attack, where a single attacker is controlling multiple botnets in the cloud and trying to attack one target, a server, from serving a legitimate user. So we want to avoid this, and like we are not avoiding it as in like we are stopping it. We're just, so if there is something, we see something similar to this, then we'll raise a flag and say, okay, there might be something suspicious here. And when that happens, then like there's alarm system, and like it goes on, and other algorithm might take care of it. But we are the first line who would just stop from it to be happening. So let me reiterate. So flow cardinality is a number of distinct attributes within a flow, and getting all, so and in network there is not only one flow, there is multiple of these flows. So getting estimate for each of the flows is like flow cardinality estimation. Are we good? Yes.
So like by distinct attributes, is that just like distinct number of sources, or is like what's in the packet count as an attribute?
So it differs based on what task you are achieving. I'll point to you in the next slide maybe. Yes. So here. So like you said, like it differs from task to task, right? For super spreader, we are looking at how many source IP is contacting different destinations, right? And for DDoS attack that we saw, like one destination IP getting contacted by many sources. So it differs on that aspect. And further, like, so like port scan would be flow level, the flow level would be one, and then attribute would be the same. But in the back of hand, behind the scene, it would be using the same algorithm, but it would differ based on what task you are trying to achieve. Any questions so far? Moving on. So there is two directions that we can take when we are trying to do flow cardinality estimation. The first is sampling. So sampling, like it means we are trying to get a subset of packets or subset of data from over a raw data stream. Like in this figure, we can see there is 36 packet stream here, and we only get 9 of them, if I'm correct. Yeah, 8 of them from those 36, right? And the next is we can use sketch, which is compact data structure, right? And like let me reiterate that switches are very limited in memory. So we want our algorithm to be very compact, so it does not use up the resources of switch. So this is a simple example of count win sketch, where it would use tables to compress the data stream that we get. Right? Any questions? No. Okay. So flow cardinality, as I mentioned earlier, is the number of distinct attributes within a flow. Right? So traditional, like in traditional concept, there is two main ways we can do sampling. One is systematic sampling, where we would select packets with a probability of P in a certain interval, or with some deterministic rule. Say, like we have a packet that arrives, we select that packet in every 100 packets. So that's systematic sampling. So there is a probability peak, and we select packets like that. For random sampling, it's slightly different from systematic sampling in the sense that there is still a probability of P, but each packet has an independent chance of getting selected, right? And there is one core problem here. So what happens is, like when we do traditional sampling, like systematic or random sampling, one problem is we can't remove duplicates. Like since each packet has a probability of being selected, it does not make sure that we select, we do not know that it will remove duplicates or not. So we need a way to remove these duplicates, and this brings us to non-duplicate sampling on the next slide. All right. Right. So the formal definition of non-duplicate sampling is for each packet that we receive, we want the probability of probability P that each packet that will be selected in its first occurrence, but for all other subsequent occurrence, we'll remove it. We'll not care about it because flow cardinality only wants distinct packets. So that is our main goal. We do not want duplicates to be in our system, right? So in this example here, to the top, we have 5 packets. So 2 of them has blue attribute, 3 of them has green attribute, right? So the chance of getting selected for blue and green is like 50% according to the probability that we set in this diagram. So blue might be selected here, but it's not because the packet is independently, it has an independent probability of getting chance selected. But here we have green packet that is selected, right? But the thing with the previous sampling is like we might select like 1 blue and then 2 green packets, and that is not useful for our task. So we want to avoid that. Right? So here are some of the prior works, Bloom filter and two-phase protocol that does non-duplicate sampling, and they try to optimize the flow cardinality estimates by going into different protocols. I'll not go over them here, but these are some of the non-duplicate sampling algorithms. All right, so what we have learned so far, quick recap. So in traditional sampling, what happens is like it does not remove duplicates, right? We might see packets that are sampled from a bigger stream getting sampled twice or thrice. So that is not useful. But whereas non-duplicate sampling, it will remove all the duplicates, right? And the traditional sampling is good for getting general statistics, but non-duplicate sampling is good for our flow cardinality estimation task, right? So NDS effectively handles duplicate item, making cardinality counting much easier and much accurate than other methods. Any questions? All right. So now it brings us to this stage where non-duplicate sampling, when we do non-duplicate sampling, like we see different kinds of duplicate in the network. The first thing is like we have intra-point duplicates. Suppose there is a node, like in this figure, let's consider P0 as one of the nodes that we'll be looking at. In that node, we see X0, X2, X2 appearing twice. X2 is appearing twice in that node, right? So when that happens, we see that is a duplicate. So that is called intra-point duplicates, right? For the next one, now we have this topology, fully connected topology, where X0 is traveling from P0 to P1 to P2, right? So when X0 travels from X0, in the beginning, P0 is a global new packet. But when it reaches P1, it's not global new packet because it has already been seen before by P0, right? And this, if we try to count it again, then it will cause some estimation error. So we want to avoid that. And similarly, it goes to P2, and it might be counted double. So it's not useful for us. And traditional non-duplicate sampling cannot handle inter-point duplicates effectively. So we need a version of non-duplicate sampling that is distributed, and we can remove both kind of duplicates, not just intra-point duplicates. So DNDS brings us to the formal definition of DNDS, where we, like among the big packet stream, we would sample it with probability P, and we sample packet with probability P, and remove all the global appearance, not just the local appearance, right? And the key properties about DNDS is like every packet has a chance of getting sampled with the same probability P, and it removes both kind of duplicate intra-point and intra-point duplicates. Right? Any questions? Okay. So before going into the design, DNDS design that we have, I want to show you one work that handles just NDS, non-duplicate sampling, not network-wide non-duplicate sampling. So this design is called virtual filter. So the figure on the top shows the design. So it consists of bitmap B. The first M bit is real bit. The last part is virtual bit, right? So the first bit, the good thing about this algorithm is only the first M bit is real part. The rest is just ignored usually. I'll go brief over this in the next slide, but only M bits is real and no virtual bit is stored. So yeah. And okay, so this is the algorithm of virtual filter. So when a packet X arrives at the measurement point, then we simply hash using an independent hash function hx, and the range of hx would be all of the bitmap, not just the M bit. It will be all of the bitmap that I showed you in the previous slide here. Oh. So just not M, it will be the whole M prime. Right. So we'll be using independent hash function, and good thing about this algorithm is we'll just be using one hash function per packet. And so the first step is checking if it falls in the real part or the virtual part, right? Usually when we hash the packet, if it falls in real part, then we continue with next step. But if it falls in the virtual part, we just ignore the packet without considering it further. On the next step, since it consists of bitmap and it falls in the real part, then the bit, we check the bit of that index. So like if the bit of that index is set to 0, that means if it was 0, that means there was no packet that was seen before. And this is a new packet that has had in that measurement point. Right? And there can be a scenario where another packet, say packet X is coming beforehand, and that's set at bit to 1. When packet Y arrives, due to hash collision, it might also be hashed to the same position. So we are expecting that hash collision, and we have some error bound we are expecting some errors in that. So when we get to step 2, we just check if the value in that index is 0 or 1. If it's 0, that means it's a new packet. If it's 1, that means it is a duplicate packet. So we do not proceed further. And once we pass that step 2, then we get to step we set the value of that index to 1, marking that packet has been seen now. So any further new future packet that arrives, then it will be blocked in this step. Right? So in this way, we remove duplicates effectively for local duplicates. And finally, we use compensating sampling, which I'll talk about it in the next slide, like how that came through. So we use this compensating sampling. If it gets sampled, then we go on to recording it in like super spreader. Otherwise, it just gets dropped. Any questions on this? Okay. So, and like since this is only using one hash operation, that means it does not consume much resources. And we are using a simple bitmap. It does not consume much resources, right? All right. So this is proof of correctness for the virtual filter. So on step 1, we are checking if it falls in real part or virtual part, right? So the chances of it landing in the first M bits is M over M prime. So that's the probability of it getting passed from first step. The second step is removing the filter. So we use like in the real part we have M bits. So and in that M bits initially, like whenever the program just started, then the M bits would be all 0 in the beginning, right? So as more packet arrives, the value of that bit is set to 1. So the value of Z decreases. Where Z is the number of zeros in that real part, right? So this evolution where G decreases, right, we see the step 1 and step 2 would decrease as like more packets are yes.
What,
Yeah.
what is a 0 bit?
So in bitmap, we have ones and zeros. So z is just the variable that stores the number of zeros in that bitmap.
So where is that 0 bit? You have m prime and the portion m. First you
So
test if it's bigger than m prime, right?
uh-huh.
So you get
So-
a residual. And then you test if it's smaller than m,
Mhm.
so that in that case you drop the virtual.
Mhm.
So why would you drop the virtual? What do you mean by virtual?
So the virtual part is like, so the idea with this is like we want to minimize the traffic volume when we are in switch, right? So when we do not want to sample every packet that we see. Some packets might have more importance, some packet might not. So if the packet arrives again, it might have a chance of getting sampled again. So we do not want to do that. That makes, and also z is the number of zeros currently in that bitmap.
All right, you hit 0 bit, and then P2 would be z over m.
Mhm.
So what is the real value of P2 here?
I think it will be more clear with example. I'll show it to you now. Okay. So the idea is like, we say we have 10 packets in here, right? So we receive x1, it falls in virtual part, it gets ignored, right? So when we receive x2, it falls in the real part, and it gets, the bit was 0 initially, it gets set to 1, and then with the compensating sampling, it will be sampled in our example, right? So this, when we set that value to 1, the z value decreases by -1. So like let's say z was in this case 10, then it will be 9. There is 9 bits that are remaining to be hashed. So the probability will decrease as more packets come in. That makes sense. Or yes. Yes. So it's one hash functions is enough for one packet. So the requirement of our design is like we use one hash function just to get the index in the virtual filter, or in the in the virtual filter, and this is not our work. This is like the prior work that was done. Okay, so coming back here, so as the value of z decreases, the sampling in P1 and P2 decreases because it's a decreasing evolution. So we need to compensate for that. So we use a function of z that will compensate the decreasing evolution, and the overall sampling probability would remain p. So that's why we need a compensating sampling in step 3. Right?
So what will your P2 be? Z over n. What
Mhm.
is the value of z?
So z is just the number of zeros in the bitmap, and then m is the size of the real part, right?
Right.
And then
What z 0?
no, z would be initially it would be m, but as like more packets gets hashed, it would be m minus 1, m minus 2, m minus 3. So initially the size of real part is m, right? And there is m indexes in that bitmap. So initially the z would be m, z equals to m, right? So when more packets get hashed and it gets marked as it has been seen and gets sampled, the bit will be set to 1, right?
Where if it's a bit, then it's either 0 or 1.
Yeah.
Binary, right?
Mhm.
So for me, if it's 0, 0 bit means 0. No,
I think
probably
might-
1. All right, I don't know how you define your 0 bit. But if it's 0, then your P2 would be 0.
Oh no, so 0 bit is just a way of saying like, oh sorry. So 0 bit is like counting, so this is just a variable that stores how many 0 bit is in that current bitmap. So in this case, like initially, like this would have m number of bits that are 0 bit.
All right.
Like as time goes on, that bit will be set to 1, right? And then the value of z decreases. I think I need to word that better. This 0 bit, yeah. So this is just a variable z that stores the number of 0 bit currently in the bitmap in real part.
Number of 0 bits.
Yes.
All
I think I need to rephrase that.
I see.
Question here, sir? No?
Okay. Yeah. Yeah. Thank you.
All right, so your Z is actually the number of zeros.
Yeah, so I just wanted to, I think I need to rephrase this saying that like we see if it hits the 0 bit, then it's a duplicate, but I can rephrase that, yes. Thank you. So the example here, we have 10 packets, x1, x3, x4, x7, x9, and x10 all falls, when we hash, it falls in the virtual region of the bitmap. So we do not continue with those packets, it just drops. Right? So the next packet we have is x2. When it comes, the initial value will be 0 here. And then when it sees the value is 0, we set that bit to 1. And when we set the bit to 1, in step 3, it still might have a chance of getting not sampled because of the probability. But here it gets sampled for our example. On the next one, we receive x2 again, right? So when that packet arrives again, on step 2, the bit has already been set to 1. So it just gets dropped as a duplicate packet. And for x5, since it's a new packet, it hashed here, it will be set to 1. And it will get sampled, and it will be processed normally. But another example is x6, where it passes step 1, 2, right? And in step 3, it might be dropped because of the compensating sampling probability. Mm-hmm.
Yeah. So what is the intuition behind multiplying different probabilities in the previous slide? Could you just go on that? Just simple explanation.
So, like each step has a probability. So I'll show you a parameter setting for this one. But so overall, the sampling probability is set by the user, like depending on what traffic we are expecting for the network. So if the traffic is high, then we'll be tough on sampling, like the p-value would be low because we do not want all packets to be sampled. And the multiplication is just, I think it's multiplicative property of all the steps. So we do multiplication to get overall sampling to be p. And we also do some tests. And in the paper also they do some tests where they do 10 different experiments, like with different data stream. And their actual sampling, if it's 0.5, it's very close to 0.5 on most of them because it deviates obviously in real scenario.
Thank you.
Okay, so with this brings us to our design of distributed non-duplicate sampling. So in DNDS, our design is very similar to virtual filter, but it's slightly different in the sense that we are doing distributed sampling, like we are trying to remove both kind of duplicates, right? So what we do is we segment our real part into different segment. So this segment belongs to that measurement point, okay? So this belongs to B0 measurement point. 0 measurement point, 1 measurement point, 2, and then U measurement point. So it is scalable up to like bigger network system, which I explain the later side. But the key idea of this is real part, virtual part. The first M bits is real part, which is the real memory. The M minus M prime is virtual part, which we do not store. It's just there to do the sampling, so not all the packets are sampled. Okay. Okay. So on our design, so the first step is same. So we would see if the packet falls in real part or virtual part. So if it falls in real part, then it gets sampled. Otherwise, it gets dropped. The second is filtering local duplicates. So say we have a packet that arrived at. So we have 4 of them here, right? So it arrived here, and this switch is switch 1, but this arrived at switch 0 segment. So that means this is the first arrival of that segment, and it gets passed through the second step. But for the third step that we added in our design, like when it arrives here, we need to see if that packet falls in that switch segment or not. So if it does not fall in that segment, so this is switch 2, it arrived in switch 1 position, then it will be directed to another switch that it belongs to and processed there. And then same thing with the sampling, probability compensating sampling, so we can compensate for the decreasing function of Z, or decreasing value of Z over time. And this compensating probability is always some function of Z, so we need to say how many Z, or overall the probability decreases like from step 1 to 3. So we want that not to happen. So the overall sampling probability in a bigger picture remains P. Yes.
I don't really see what the main difference between step 2 and step 3 is. Like I see that they're looking at different things, but how exactly are they different?
So if you remember, the key concept of non-duplicate sampling is removing duplicates, right? And then there is 2 kinds of duplicates. The first duplicate is intra-point, which is 1 point, right? But in distributed settings, we want both of them to be gone. So from previous one, the non-duplicate virtual filter, what they did was they only removed part of the duplicate, but it was not suitable for distributed settings. And what step 2 does is similar to what they do, but after step 2, we check if the segment falls in that switch or not. If it does not fall, in step 3, we say, okay, we redirect the packet. And I'll show you an example of how it's done exactly. But yeah.
So so I understand each switch or each measurement point stores its own real part of the virtual bitmap.
Right.
And so it can only really sample a select number of packets because it can only certain ones will hash that small section.
Right.
So is there a global bitmap being stored on a different switch that has all of it?
Yes. So all of the switches will be deployed with. So I'll come back to this example. All of the switches will be deployed with a bitmap, right? And so in this case we have 3 switches, and so the first 2 bits are belonging to P0. Second is belonging to P1 and P2, but each of them will know the segment, which switch belongs to which segment. That's the only key difference, right? So, yeah, we are in examples. So let's start. So X1, X3, X4, X7, X9, and X10 gets dropped because it falls in the virtual part. So now X2, it appears in P1 switch, right? So when it appears in P1 switch, what happens is this is the first appearance of X1, right? So this is the first appearance of X1 here. And when it sees the previous value was 0, it will set that bit to 1 and it gets sampled on the first run. Okay? Now X2 arrives again, but not in switch 1. It arrives in switch 2, right? So when that happens, we know, because this switch has not seen that X2 packet before. So what happens is when x2 arrives, the bit is set to 0 in step 2, and so it will pass step 2. So, and by setting that bit to 1. So what happens is, and we check if this bit falls to the second switch 2. No, it falls for switch 1. So it goes to redirect the packet, and when it gets here, we get to step 3 in that process, but the packet gets dropped because it's local duplicate. And this way we know this global duplicate is removed. Right? Does that explain?
So basically, the switch knows which other switches have like that same real part in the bitmap.
Yes.
And then it checks with them.
Yes.
So basically, okay, well, I haven't seen this before. Have you seen this before?
Yes.
And they say yes, block it.
Yeah, so good thing about this is like it will only check for one of the, so it will check m times, not necessarily m times, it will check for the first local appearance, we will not check for the local duplicate again. Okay. And so x5 and x8 get comes here, so, it belongs to that segment, so it does not need redirection, right? And it gets sampled. X8 comes in switch 0, but it falls in the switch 2. So it has to be redirected, and then it gets sampled. Right? And X6, for example, where is X6? Here. So X6 gets here, and even if it's a new packet, even if its bit is just in view now, it might be blocked in step 4. And that's for saying every packet will be sampled with probability P. Any questions on this? Okay. And this is the correctness theorem, which is similar to their step 1. We just check if it falls in real part or virtual part. Step 2 checks if the bit is hashed or not, a bit is set to 1 or not. If it's set to 1, then this G decreases over time. And so we need a compensating probability for this. And a core thing about this is in each switch, if the sampling probability, say, for the entire distributed network system is P, then for, say, we have 3 switches, then a switch sampling probability would be P over 3. Right? And then if we just take the overall sum of those switches sampling probability, we get P. So I think Ali's question was this. So for defining the optimal parameter setting M and M prime, we use the number of distinct packets that is expected in the traffic, and sampling probability P is how we would sample the packet depending on the traffic pattern. And so the P value is compared with the 1 over E. So when that happens, we set M prime to be N, so the size of the volume. Otherwise, we follow this one. And this will help us optimize the memory uses of the switch. And so for our design to get the spread measurement, flow spread measurement task, cardinality estimation task, we did 2 models. One of them was on-chip, off-chip model. The next one is entirely on-chip. So what that means is we would use suppose we are using a switch. So we deploy our DNDS, distributed non-duplicating sampling in on-chip memory, SRAM, like in the switch. Otherwise, and the hash table would be completely off-chip. We are assuming that we have unlimited memory for off-chip. And this is especially useful if we want to get a better estimate for offline analysis. And it has higher accuracy, as I'll show you later in the experiment section. But for on-chip memory, we are using DNDS with CU sketch. So CU is a simple data structure which contains D rows and columns, right? And what happens is whenever packet is hashed, it's hashed multiple times in this scenario. So we'll hash we'll use D hash function to hash here. But since the C structure is very compact, it's efficient to store both of them in on chip. And the advantage about this design is we can get real-time estimate. It's slightly not good as on chip, off chip, because they are using unlimited memory for storage, but it's more memory efficient. So this is how you would get the value from hash table when you are querying it, and this is how you would get the value from CU sketch. So we'd check all the if we have 4 columns, then we check 4 columns value, and then we get the minimum, and that will be the estimate for the CU for the spread measurement task. Okay, oops, I think I went to the next slide. Yeah. So for our experimental setting, we use 2 models that I just showed you earlier. For the baseline state of the art, we use vSketch HLL, Sketch HLL, and Aroma. For our data set, we used Kaita dataset from 2019. We used 10 traces of it. It's containing about 20 million packets, and roughly 430K distinct packets from each trace. So for our experiment, the flow label is defined as destination IP. Attribute is defined as source IP, right? And we use this matrix, absolute error and maximum supported line rate, millions of packets per second, and check the memory efficiency. So the first result I want to show you is redirection ratio. So in step 3, if it does not belong to that segment, then we obviously redirect the packet to other switch, right? So when that happens, and like the result shows like very minimal amount of packets are getting redirected. This is because there is 2 reasons. The first is like in step 1 and step 2, those 2 packets are getting blocked, and not all the packets are going from step 1 and step 2, right? And the next reason is whenever we send packet from one switch to another switch, we'll not send in the entire packet. That will cause overhead. So we'll just send, like for this example, we'll just send source IP and destination IP to the next switch. So it will not cause overhead in our network. Okay? And this is very minimal, like when we compare the overhead with other algorithm. Okay, so I'll quickly. So this is accuracy under 1 MB. So this is the design of hash table. This is the design of CU, Aroma, vSketch, RSketch. So the closer the dot points are to the diagonal line, purple line, it's more accurate. So in a hash table, you can see most of the flows, like a little bit here, but most of the flows are concentrated toward the diagonal line. Whereas for our CU design, which is expected because it is compact, it will compress the estimate. So it's more scattered outward, and as it goes from medium to larger flows, it's more concentrated toward the diagonal line, because CU is better for getting estimate of higher flows. And other sketches, some of them do well, some of them are not that good. And the next table I'll be showing is absolute error detection in ranges for flow cardinality estimate. So from 0 to 10, as you can see, our hash table, because it's using unlimited memory, it's doing very good compared to other design. And our design also is comparable with others for CU if we are implementing completely on chip. So, and hash table outperforms all of them, whereas count update is good for medium to large flows. And yeah, and we can see 10x improvement over other sketch-based method, and CU would outperform like most of the state of the art in like medium to larger flows. So this is extension of our work that we are working on right now. So super spreader identification, so where we identify the top the flows that are exceeding this threshold. So this table shows the true count of the super spreader. So threshold 200, there's 146 flows that exist, and number of false positive is just saying that. So number of false positive is the flows that does not belong, is exceeding the threshold but does not belong there, and false negative is the other way. But our design mostly outperforms most of them. So this is also extension work where you are implementing our design in hardware setting, especially in P4 switch. So we are using P4 2-pin switch especially because they are better compatible to program in data plane. So there are 6 phases for this algorithm. The parsing header, so we parse header to extract the required information like source IP, destination IP, checking the computing the hash computation that will take. There is a CRC32, CRC16 hash function available in P4, so I'm using that. And checking bitmap is just register read write operation. So these two would go in one, and then if it does not belong there, the forwarding logic would send the packet to the responsible switch, and then finally the sampling decision. So that is the 4 pipeline, and we tested this in 2 different topology. The first is linear topology, and the next is fully connected topology, right? So the good thing about this is this is less costly. This is more costly, and has to do forwarding for S1, but here every switch is connected to each other, so no forwarding needs to be done by other switch. Right. So here I present the same table that I showed you earlier about redirection, but this is in hardware setting, where we can see for the linear topology there is slight variance in the S2 because it's forwarding for S1, also S3. If S3 gets packet for S1, then it has to go through this way. So there is slight increment in the percentage of forwarding, but overall it stays the same. Like it's very minimal change. So, and for fully connected, the design, what we saw in the software setting, we were able to see it in fully connected, right? And so this is the throughput that we achieved. Like we achieved 90 to 96% depending on the sampling probability. So I think it's almost in the line rate of most of the hardware implementation. Okay. Let me, and then, yeah. That is just the conclusion, and here are some of my work. Thank you. Any questions?